Okay, well, let's see if I can figure this out. Okay, so I also wanted to mention that I've got a couple of my team members here. I've got Igor Kostyuk, who is the lead developer on the project, Roman Grubnik, who's the lead deep learning programmer on the project, and Yuri Milnov, who did all of our QA. So if you have any technical questions, you can certainly ask me, but they're here to help you as well. So what are we talking about? Okay, so the fundamental assumption here is not to attack or discredit any of the things that we've been talking about today. I think that everybody knows their craft very well. It's really the supposition that to really model artificial intelligence, in a robotic sense, in a general cognitive sense, in a video game sense, that if you really want to have a processing power and a decision capability that approximates the human condition, then you just can't sit there and hand code the variables and hand code the rules. The complexity is just too high. Now, I certainly would agree with some of my colleagues that there may be some predicate calculus or some sort of optimal way of modeling things or some way to do collapsible PDE matrices or something along those lines. But for the most part, we're just assuming that there is a computational cliff or a complexity cliff that one reaches. So the takeaway from this slide is saying that what specifically is tough about the gaming space or the dimensionality space of robotics. What's tough about it is, as everybody in the room knows, a 4D spatiotemporal problem of you've got a pattern stimulus coming in, and that's what makes it fun, is that the human brain is very well accustomed to see that pattern stimulus come in. And actually the brain tends to cycle, I think, at 60 hertz. So you tend to, or 60 to 120 hertz. So that's one of the reasons that your monitors are configured the way they are, so that, versus a canine, right? And so your brain is essentially flickering. My friends joked as flicker vision, but you're flickering and you're sampling at really fast speeds. And I mean you, not the game bot, right? You are sampling me at very high, at a high frequency. And then you are essentially making calculations in the sub-second time period and making assessments about my behavior and that sort of thing. Okay, so that's sort of the opening. Again, I'm arguing that it's a degree of freedom problem and that it's computationally very difficult to do things with rule systems. And this last point about complexity collapse is to say that I see this. So in my job as an artificial intelligence guy, I touch a lot of industries, and I see this in every single industry. And every single industry will tell you, well, this is all we can do right now. And eventually it gets better and better, and there's abstraction gets higher and higher, and more tasks are able to be completed. But for the most part, we're always where we are right now. And so that is ultimately a complexity collapse of your capability to process information and to do tasks. So that's sort of the overall theoretics. I'll get a little bit more applied. So, okay, so in the case of game playing, right, more germane to why we're here, in the case of game playing, people have really talked about this in AI. They've been talking about this in two different capacities. One has been the artificial, general game playing conferences, and now Diego's, actively involved in this area. And there's also the sort of biologically inspired computing movement, which is a lot of neurological bases and sampling and working with neural labs on, looking at how the brain makes decisions. A key, just a small citation here is this artificial learning environment, and it's just a footnote, but ultimately when we get to the discussion of DeepMind, you'll see that they've sort of corralled a lot of these resources to holistically make the solution that you probably saw in Nature and that caused waves last year. Okay, so ultimately what we're talking about is modeling the human cognitive process, okay? And in the field of cortical computing, there were actually strides in the 70s, in the late 50s and 70s, for figuring out so there was obviously machine learning. One of my old advisors, Marvin Minsky, I think came up with a neural network in 1951. And so there was neural networks in the early 50s, but then this sort of biologically inspired movement sort of caught on, and a little bit of mathematical modeling of physiological process, and specifically, again, as it relates to games, visual stimuli and real-time visual stimuli was modeled by Fukushima. So, and again, this is sort of a boring historical footnote, except for that when we, hopefully by the end of the talk, when we add all of this together, you'll see, in the Kaiser Sose way of things that this is how DeepMind has been able to deliver what they've been able to deliver. So, Fukushima and others were able to do sort of basic prototyping and primitive extraction out of the way that the cat and mammals processed visual information, which led us to a guy, Jeff Hinton, in the early 80s, and another guy, Jan LeCun, who both cited heavily in their early work, the biologically inspired models of Fukushima and these other guys. They said, okay, well, we want to take the Fukushima work, and we want to take this earlier work, and we want to build a machine learning classifier that has similar components and similar attributes. The similar attributes being a highly hierarchical neural network that is a little bit more complex than the sort of off-the-shelf neural network you're used to. So that's all fine and good, right? Deep learning was sort of taking off in the early 2000s. People were really getting into it. They felt like it was more biologically feasible. And again, that's been sort of my previous slides. And they're saying like, okay, it's biologically feasible. Who cares, right? Well, along comes this guy. And so Alex Krzyzewski, and I'm probably botching the name, but Alex comes along and employs a synthesis classifier, which is basically a LeCun-based design with a hint, and he's one of Hinton's guys, and he's able to boost performance, and this classifier is considered state-of-the-art, hands down. Nobody's been able to really do anything. I mean, people have optimized a few percentage points here and there, but again, this is sort of in the object recognition space. And you could say, oh, okay, well, what is a deep learner? Okay, this picture is actually, it's a lot of color, but it really, shows you the power of a deep learner, which is just to sit there and literally through layer upon layer abstract out features. So one of, I think, Alex's quotes, or one of the developers of deep learning, that feature learning is so 90s, right? So feature selection is so 90s. So you've got the raw data sets here. There's an emergent clustering that occurs, and then as progression occurs, you end up with something which is known as a Gabor filter, okay, which is essentially the RGB triage of a stimulus. So this is an actual representation of a real-time deep learning network topology. There's a really great paper by Matt Zeller that I recommend. He's the CEO now of Clarify, which is a startup in cognitive processing. But, okay, so that's all fine and good. That was sort of our deep learning primer. The key is, this is all about, this is now saying that what we've been talking about, where I've taken you, is to a human level of object recognition. Okay, so now we're at a human level of object recognition. We're not at a human level of action. However, as we know in video games, it's highly video and auditory, right? So now we enter in reinforcement learning. Okay, reinforcement learning is a technique for training action, and ultimately, the simple way to describe it is that you're constantly sampling the game space I was talking about, the temporal game space, and you are looking for sort of incremental improvements, and you are ultimately going to optimize towards either a local or a global policy. In other words, like incremental sort of tessellations to the underlying neural network. To my embarrassment, when I started researching these slides for you, I realized that I was taught how to use reinforcement learning to modify neural networks in school, and I had forgotten it. So that's actually the Bertsikis quote, Bertsikis book from a long time ago. Okay, so why does that matter, or who cares, right? Well, so now you've got human-level object recognition. You've got a plausible, realistic way of optimizing that recognition. So the DeepMind folks, who were acquired for something like 400,000 pounds by Google with no product, no customers, and a archive paper. The DeepMind folks came up with the obvious mathematical observation that I'm telling you now, which is that reinforcement learning's been around for a long time, right? I mean, I was taught that, I'd forgotten that. I mean, it's been around for a while. Reinforcement learning in neural networks and Markov decision processes was around, but reinforcement learning plus the paradigm of this Krzyzewski deep learning now gave you a human capability to, in real time, recognize objects and to sort of train and act on a system in real time. So I'll just leave this slide on the board for a second, and here's a key thing for everybody that's in the room that's a game developer, that with one set of hyperparameters, so in other words, they've built their system and then they came up with a decent configuration. With one set of parameters, 49 different games, 49 different modalities, human level or better gaming prowess. That's kind of cool. I guess that's what gets you bought for a lot of money. So why this talk? Why am I here? Because I'm not from DeepMind, and it doesn't. I didn't get the money. So why am I here? Why am I talking about this? Well, my team sitting over here, ultimately, we were very impressed with the paper as well. This was prior to the purchase. I'd been doing some DoD work in temporal psychological assessment, and so I recognized that real-time, decision triage was something that was, professionally of interest to me, and it was certainly of interest to my team. So we speculated that, the source code wasn't available, and with Google's acquisition of the company, that the source code would not be available. Turns out that now in 2015, the source code is available with the Nature paper, but not for you. So it's a restricted Nature-only read. It's not commercially available, and it's not open source. It's just some sort of demonstration use case. So we kind of thought that some it's not nefarious, but some sort of restriction would occur. So we wanted to, we were reasonable math guys, so we wanted to reverse engineer the solution. The solution that the DeepMind guys, the good news for those of you who are Lua programmers is that the DeepMind folks programmed their system in Lua, and they used this middleware for Python to CUDA called Torch. And so if you don't mind suffering through that, then and you don't mind recoding it with different variable names and creating a whole new environment, then be my guest, get the Nature paper, and you're off and running. But from scratch, because we didn't have the Nature paper, we did a Python implementation, and we decided to Apache license it. So Apache license, for those of you, most people in the room understand that Apache license is totally unrestricted. Just, we appreciate the author attribution. It's not GPL, so you don't have to contribute code back. Do whatever you want, use it in your commercial games. I'm not Google, so I don't have the patents. So, if they come knocking with the patent law, then that's a different story. The reason I bring that up is because that was actually news recently, was that Google has started a massive patenting in machine learning, but I digress. So what does our application look like? Okay, well, we had dissected the paper back beginning of 2014, or by mid 2014. We built a wrapper or we built a paradigm. Igor, sitting right there, built the wrapper and the windowing environment. I think these are probably series diagrams. And Roman had done a lot of deep learning, and so they were able to literally wrap the deep learning and do a lot of parameter testing, and to create a CUDA-based GPU implementation, which we're happy to say and proud to say here at this conference, we're at a stable beta. So we're at a point where we had some memory leaks and just sort of normal development pain. And we got to a point where the system doesn't crash, the system does pretty well. I hope that this video works. There's no sound, so. Look good. I'm seeing something different. Well, it works, trust me. Yeah, if we can't get it to work, you can always come see the video. Yeah, is it not supposed to be? Right, so how do I switch? Okay, well, that's great. Yeah, well, we have the video, and we're happy to show any of you guys the video. The video is cool. It basically shows that over 20 hours, the thing goes from completely idiotic and not at a human level to playing Breakout definitely better than I do. And I'm not bad, I mean, but it's definitely better than I am. So, and again, this is after 20 hours of training. Am I correct, Igor? 20? Yeah. So, a key slide here is, so with boxing in the arcade learning environment, you could say, how does a human get negative points? Well, apparently, like in this particular arcade game, you're subtracting points from your adversary. There are two takeaways from this slide. One, that maybe three. In Space Invaders, you've got humans beating our current system in that 20-hour training epoch. The reason is probably because Space Invaders is a little bit more complicated in terms of look-ahead and look-ahead strategy. Multiple things, sort of temporally coming down, multiple types of adversaries. Obviously, with Breakout, you're seeing that the DRL solution is twice as good, nearly twice as good as a human. And with boxing, it's damn good because it's all sort of about reactivity. So there's not a high amount of complexity. It's just the machine is just beating you up. Literally, it's just it's figured out the game, and it's just gonna beat you down. So that's the first takeaway. The second takeaway, and I think this is the most important takeaway, is that this is one parameter setting, and it learns the game space. So we're not messing with it for boxing. We're not messing with it. We have one parameter setting for all games. We're not the DeepMind team, so we didn't do 49 games, and we don't have that level of comparative robustness. But we have some highly encouraging samples. So, great. Okay. So the announcement here, which is just an informal announcement, is that we coded it up, we've tested it, it's stable, it beats humans on a couple games, it's near human level on a few, and we have put a open source site together with all the licensing terms, and that's again with just the open licensing terms. There's links to GitHub, there's pre-configured VMs, there's pretty much everything hopefully that you need to get started, and you don't owe us a thing. We're just maybe Google knocks on my door later, but the point is that for now this is open science, and it's definitely a cool development for you. The only plug that I'll give you is that I've integrated this into my commercial system. So, we have a commercial configured support version, which basically is just a pre-configured network where we run it on a 200 GPU grid, where we've optimized the heck out of it, and we're making it available to our customers. Okay, so final points. What are we up to now? Well, if this talk interested you at all, I would say that what we're up to now, we're doing hyperparameter studies, which is just kind of what I mentioned, that we've got it stable. We understand our parameters pretty well, but across different node types, across different network topologies, as a lot of the people have talked about in previous talks today, what's the memory management model look like, right? So we can train on this gigantic cluster, but then when we actually abstract out the neural network and then we put it on the local desktop, how much memory does that use? Is that tractable from an agent standpoint? Is that tractable from a embedding into a larger application standpoint? So those are some of the things that we're exploring right now. That kind of is covered by GPU farm optimization. Complex games. So obviously, when we were planning this talk, when Diego and I were planning this talk, the question was, are you guys, what games are you supporting and that sort of thing? I mean, the key thing is the ATARI scenario is just what we were doing because the DeepMind guys, that's what they used, was this ALE environment for their nature paper. We were just trying to show you how you could do the same thing. We're certainly moving on to three-dimensional environments, more complex environments. And then, something that's a little bit more germane to, the gaming industry is we're looking at build-outs, right? So if you can build 3D environments and the agent does decently well, does it do well with a sword? Does it do well with spells? Like that sort of thing. And then the last point is my personal interest, which is transfer learning. I led a group, a college research group in this topic. It's not trivial. It's a challenge. I would say that my group actually wasn't successful at the time when we were trying to come up with some sort of global theory for transfer learning. But transfer learning is the simple act of one-shot learning or whatever you want to call it, is the simple act of knowing what to do in a situation you've never encountered before, right? We as humans do this they theorize sort of a coalescing of archetypal opinions, right? We say, well, it is a elephant-looking thing that does this, so we sort of ensemble attributes. But ultimately, how can we apply transfer learning, and how can we apply it to this paradigm? Because if we can apply it to this paradigm, then the thing will understand what to do versus this Pavlovian sort of hyperreactivity that the math does now. So, like I said, if there's any questions, I'm here, and so is my team. So the question is, how long before it learns League of Legends, for example? I'm not sure, because I think that because of this transfer learning issue, that I think that my guess would be that you'd get this sort of basic strategy very quickly, maybe 20 hours, right? Like within a day. But then complex strategies where you're sort of, the scenario is, I do some delayed gratification strategy. Many strategy games have a delayed gratification model where you implicitly sacrifice troops or you do something like that. And this system, is very hyper-reactive and wouldn't, probably too impulsive for that sort of thing. So I think you need some sort of stepping function or, some look ahead, as Simon's point.
Yeah, thanks. It's a really, really interesting talk. So one game that you might think about trying next would be something like Pac-Man from the Atari series, because the deep learning system, the DeepMind system, didn't perform very well on that. And one of the reasons is that you need a little bit of strategy. So it's not just, it is kind of reactive, but it's reactive in a more complicated way. So you've got to figure out where the ghosts are going to go and figure out which pills you need to eat. There's some route planning involved as well. And I think one really fascinating thing is this architecture able to solve it with more tweaking and more effort, or is it somehow out of the grasp of this sort of thing, and you need something more. And I think, I don't know if anybody knows the answer to that yet, but I'd be interested in your insights.
Yeah, no, I think that's the, I couldn't have said it better myself, that's the crux of what we're interested in, is can you modularize, so we built a very modular system that you can use today, right? But is there a sort of a modularity that lends itself to complex sort of, stepping function sort of, where the stepping function goes out and does some planning like we saw earlier today, or is this sort of too brittle, like you said? So I think it's a great question, and I think that's exactly in line with the theoretical questions that we're asking now. And it's also important for artificial intelligence in general in society, right? I mean, certainly games are exciting and they're a great platform to discover these things. But if you can understand modalities you've never seen before as an AI, then you really truly have a robot scientist, right? Because then you can sort of hypothesize and test your solutions without actually having seen data that's exactly, in line.
Actually, I was just reading the new paper from DeepMind. They actually cracked Pac-Man about a month ago. And it's from the results, you can find it's post-human level now. So that's quite interesting in its own. But just because I think it's the key issue with all of this beautiful tech, could you elaborate a bit more on the patent issue? Because wouldn't now looming the patent that Google actually owns the IP of all this stuff basically kill it completely in its birth, basically?
In theory, yes. So you and I were talking at lunch about how some of the latest news is that Google has put an aggressive patent portfolio together based on all of Jeff Hinton's work, and because Jeff Hinton's now joined Google. But there's also been sort of like base classification and some patents that are kind of ridiculous. My read on that, my optimistic read on that, is that Google tends to be a defensive patent operation. So my optimistic read would that they would go after giants and they wouldn't go after the research community. I'm not a patent lawyer, but I have spent too much money on them, and I can tell you that the transactional nature of them putting out the Lua code for the community to see definitely questions whether or not as a prior art to, the patents have been filed, but the patents have not been issued. So everybody, you can use this all day long now, and there's no patent protection for Google yet. It's just that the way the patent process works, for those of you that don't know, usually when you submit in the United States or other countries, you've got about a year and a half. You submit, and then after about a year and a half, it's public knowledge, and then maybe after short order, within 6 months to another year or two, you get the patent or you get rejected, right? So people know what patents are looming. You can do a secret patent that costs more money, et cetera. But these are not secret patents, and so for now, you're protected. When Google gets those patents, it'll certainly be big news. I agree with you as to what their intention is. Is their intention to go after people, or is their intention to be purely defensive because IBM and Microsoft are aggressive? I don't know. I'm not at Google, so I'm hoping that we didn't waste our time, but it was certainly a cool exercise and a cool platform.
I just want to come back to the point about Pac-Man. So I hadn't seen that paper, and I've got a slide on it in my talk, which is now obsolete. But one other thing that's worth keeping in mind about the ATARI learning environment is that the games are largely deterministic. And so, although it's cracked that version of Pac-Man, there's something we've been running previously, which was the Pac-Man versus Ghost Teams competition, where people could submit any sort of Ghost team to play against any sort of Pac-Man. And it would be really interesting to try the latest DeepMind stuff on that to see how strong a player it is against various smart Ghost teams. Very, very interesting.
Great. Well, thanks again to my team, and thanks for listening.
Thank you.